once we have the idea of writing a function as the composition of two simpler functions, then our next question will be, well, if you know the derivatives of the two simpler functions, what will the derivative of the composition be? So another way of talking about one of these compositions is it's a chain. So for example, if I do f compose g of x, what I really am doing is a chain of processes. I'm starting with x, I'm putting it into g, and then I'm putting the result of that into f. Now, in this case, we've got two functions. They're nice and linear functions. In fact, I can see that the slope of the first one is m, so the slope of the inside function is m, and the slope of the outside function is this number n. So what if we compose them? What will the slope be? Well, let's see. G takes whatever you give it, and it gives back m times x plus b. And then f's job is to take whatever you give it, multiply it by n, and then add c. So I'm going to take n times mx plus b, and then I'll add c. With a little simplification, I can see that this is going to give me m times m of x plus nb plus c. Now these are constants, right? So we composed two linear functions, we got another linear function, and the slope of this function was the product of the two slopes. Now that in general is true. The slope of the composition, or the rate of change, or the derivative of the composition, slope of the composition is the product of the slopes. Okay. Now we can see that's certainly true for any two linear functions, it's just when we compose them we got the product of the slopes. But it's also going to be true for nonlinear functions, but we have to be a little bit careful. There's one little wrinkle, and that's for a nonlinear function the slope is not the same everywhere. So we've got a little issue to handle. We got to figure out which two slopes do we multiply, right? Because each function has a slope that's changing according to the position. So we'll have to work that out. But you can think of what this is saying in terms of, I have these little taffy roller machines. So I have this set of rollers set so that if I take a lump of taffy, maybe it's some distance x long, if I put it through these rollers, it gets smashed, and I've got the rollers set just wide enough so that now the taffy is coming out 2x. So we have these rollers, and they're set so that there's a stretching factor of 2. In other words, whatever the length is to begin with, you put it through these rollers, and the length afterward is going to be twice what the original length was. Okay, now let's say I have another set of rollers, and I've set these a little bit closer together so that when I run some taffy through those rollers, whatever the length is, it ends up being 3 times what it was, right? So we have this function f that stretches everything or smashes everything, so there's 3 times as long afterward. Well, imagine I set it up so that first my taffy ran through this set of rollers, and then I hooked it up so that the other set of rollers was over here, so whatever came out of that would run through this. So this first set would stretch the taffy so that it's twice as long, and then that would go into this next set of rollers, which would stretch the taffy so that it's 3 times as long as it was, right? So 3 times 2 of x, 3 times 2 times x makes it 6 times as long as it originally was in there. It makes sense that if you compose these two, you get a stretching factor of 6, right? So the first set doubles them in length, and the second set triples them in length. So derivatives are just stretching factors. In this function, if 2 points are a distance of, say, 0.1 apart, after you run them through the rollers, those 2 points will be stretched so that they're a distance of 0.2 apart, twice as far. So when you're composing functions, you're really just multiplying the stretching factors. So the derivative of the composition, if I wanted to find the derivative with respect to x of f of g of x, right, the total stretching factor would just be 6. Just multiply the 2 stretching factors. Now let's talk about some of the details that come up if the functions are non-linear. These ones were nice and linear, so there wasn't too much trouble. But let's say we've got first, we're going to start with some number x, and we're going to plug it into some function g. So g, let's say g is a non-linear function. So instead of being like a line where the slope is the same everywhere, the slope could actually be varying for this function g. Then if it's a composition, we're going to come over here and we're going to have g, and we're going to plug that into some other function f. So maybe, let's say our function f maybe looks something like this. All right, so we're going to start with some number. We're going to plug it in, and out will come g of x. And then we're going to take that output and take that number and plug it into our function f, so out comes the composition, f of g of x. We're just chaining together these two processes. Well, these are nonlinear, that's true, but if these two functions both have derivatives, they can be approximated by a tangent line. So the tangent line here would have slope that's equal to g prime of x. And the tangent line here, well, to find the slope, we could find f prime. The slope depends on where you're at. What we're plugging into f is actually g of x. So this first function is basically linear with this slope, and the second function is basically linear with the slope f prime g. So we know that if you compose two linear functions, the slope of the composition is the product of the two slopes. So if we want to find the slope of the composition, f compose g of x, then that's going to be the slope of the second function, where we're using that second function, which is at g of x, times the slope of the first function. So when you have a composition, then the derivative is the derivative of the outside function evaluated at the inside times the derivative of the inside. Another way to write this would be to say we're taking the derivative with respect to x of f of g of x. So you can see what I say when I mean inside function, right? This function g of x, here's the outside function. We're taking the derivative of the outside function, and we're using that at g. So we need to plug in g of x to find what's the slope there at g. Then we're going to multiply that by the derivative of the inside function, which is the first function. This, since we're composing or chaining two processes together, we call this the chain rule. Okay, so in general, the chain rule says this: if a function is the composition of two functions, then the derivative of that function, so h prime of x, is going to be the derivative of the outside evaluated at the inside times the derivative of the inside. We could also write that in Leibniz notation. We could say, well, we're going to take dh dx, and we're going to find df dx. How does f change with its input? But we're going to plug in g of x for that, and then we're going to multiply by dg dx. Now, another way to think about it is, if we back up and look at this picture, f is a function of g, and g is a function of x. So when we're finding this derivative, we're really finding how does f change with respect to its input, g, and then this is how does g change with respect to its input, x, right? So this is the slope, the change in output over change in input, the rise over run, for f as it depends on g, and then this is how g depends on x. So another way the chain rule gets written is in this kind of shorthand way. We find how does f change with g, and then we multiply by how g changes with x. So these two are the most common. I write this one out because it kind of gives you a sense of what the correct recipe is, right? When you're using the chain, we're going to find the derivative of the outside, evaluate it the inside, and multiply it by the derivative of the inside. Let's go ahead and do some examples so you get a sense of that. Oh. Let's go ahead and do some examples so you get a sense of that. Okay, if we look at this, we have this complicated looking function. We don't know how to take the derivative of it yet, but we can see that we can break it down as a chain of two functions we do know how to take the derivative of. So we know how to find g prime of x. That's just going to be 1 plus, let's see, this 3 comes down and makes 9x squared. We know how to find f prime because f is, the outside function is the sine, so derivative of the sine is the cosine. We can find f prime at g. Remember, g is this function x plus 3x squared, so if you give f prime x plus 3x squared, you're going to get the cosine of x plus 3x cubed is this function g. So the chain rule says if you want the derivative of the composition, then what you do is you take the derivative of the outside divided with the inside, which is cosine, right? That's derivative of the outside. Plug in the inside. Then multiply that by the derivative of the inside, which we figured out was 1 plus 9x squared. Now, just for safety's sake, so that someone doesn't come along and accidentally assume that we're taking the cosine of all of that, I don't know why they would, but accidents do happen. I'm just going to turn this around. It'd be a little bit safer to write it this way. I can multiply in any order, right? And that's what's happening here. So why don't I turn this around so it's a little bit clearer to anybody who comes along that I'm taking 1 plus 9x squared times the cosine of this whole thing, x plus 3x cubed.